In most computer systems, multiple processes can run at the same time, and they can be created and deleted as needed. So these systems need a way to dynamically create processes and terminate all once. In this part, we will look at how computer systems do such operations on processes using examples from Unix systems. So let's start with process creation. During a computer's operation, a process can create new tasks, okay? We call the process that creates other the parent process, and the new tasks are its children process. And these children can also create more tasks, forming a tree of tasks, okay? In most operating systems like Linux, Windows, tasks are given unique numbers called process identifiers. We also seen that, okay? Process identifiers. These numbers help identify each task in the system. Imagine them as a special labels for each process, okay? In Linux, processes are organized like a tree. The first task called init. So it's like the main parent. It can create different tasks like servers or programs. This task can create more tasks, forming branches in the tree. For example, in this tree structure, init has created three processes, okay? These processes. And this task can further create more tasks, building a complex tree structure, okay? So guys, imagine your computer as a big restaurant. The first member called init is like the head of the restaurant and has the ID 1. So it can bring in new members like a chef or a cleaner, giving them their own IDs. These new members can then bring in more people like a helper chef or a receptionist, and they can get their own IDs too. To see these processes running in our computer, we can use commands from this manual in Linux. This command gives a detailed list of all the active tasks in the system. So when a process creates a new one, two possibilities for execution exist. So the parent process continues executing alongside with its children. Okay. Like the parent continues to execute concurrently with its children. Or the parent process waits until some or all of its children have completed their task, okay? So also, when a new process is created, it can have two different types of relationship with its parent process, okay? The new process can either mirror the parent, contains the same program and data, or it has a new program loaded into it. In duplicate address space case, the child process is an exact copy. No, sorry. Is a copy of parent process, and it contains the same program and data. It means we have two different processes running copies of the same program. This allows easy communication between the parent and the child processes because they start with the same information, and any changes made by the child process do not affect the parent process and vice versa. And both processes continue executing at the instruction after fork. So when a new program is loaded, in this case, the child process has a completely different program loaded into its memory space compared to the parent process. It runs a distinct set of instructions and data. This means the child process operates separately from the parent process and can perform entirely different tasks. Now, to illustrate these operations, let's look at that figure. Okay. In Linux, remember that processes are identified by unique integers called process identifiers. Okay. So when a new process is created using the fork system call, so fork system call is used for process creation. Actually, after that system call, it essentially makes a copy of the parent process memory, okay? So both processes, the parent and the child, continue execution as the instruction after the fork, okay? With one difference. The return number for the fork is 0 for the new processes, the child process. And whereas the non-zero process identifier of the child is returned to the parent, okay? However, after the fork system call, one of the processes, usually the child, can use the exec system call, okay? This call loads a new program into the memory, into the child's process memory, okay? It replaces the existing program, and the new program starts executing, and the two processes, parent and child, can now operate independently. The parent process can wait for the child process to finish its task by calling wait. In summary, the fork system call creates a duplicate of the process, the parent process, and the exec system call allows a process to load a new program, making it distinct from its parent. These mechanisms enable process to communicate and then do separate tasks. And overall, it enhances the flexibility and functionality of the operating system.